Welcome to this topic of the Demystifying IPv6 course on IPv6 routing protocols. IPv6 routing protocols is just one of many topics in the Demystifying IPv6 course. In this topic, we're going to discuss RIPng, BGP4+, and OSPF version 3, which are three common routing protocols used for IPv6. To start with, RIPng, or RIP Next Generation, is defined by RFCs 2080 and 2081. In it, it describes operation which is essentially the same as RIP version 2 for IP version 4. So if you're familiar with that, you already have a head start on understanding RIPng. Although it's not backwards compatible with it, and it uses UDP port 521 instead of 520, but it also has a maximum of 15 hops. Operational procedures, timers, and stability functions are essentially the same. The message format has changed slightly to carry larger IPv6 addresses. It also supports triggered updates and split horizon with poison reverse. In other words, it will re-advertise routes back out the same interface it received them on, but it will advertise them with a hop count equal to 16. The IPv6 related functionality as it relates to RIPng. Well, RIPng is an IPv6 only protocol and uses IPv6 only for its transport. So if you're running in a dual stack environment, you'll be running RIP for IP version 4 and RIPng for IP version 6 as separate processes, often referred to as running as ships in the night. Its updates contain IPv6 prefixes and a single next hop IPv6 address. Each route table entry includes a route tag, prefix length, and metric, which is a hop count. The source of the datagram and next hop, if present, must be a linked local address. So that implies that these RIP updates that are sent are not propagated farther than any other routers on the local link. RIP updates are also sent to multicast address FF02::9, which is reserved for RIP updates. This slide depicts the RIPng packet format. Of course, RIPng is carried in IP, actually IPv6 of course, and has UDP port 521. As you can see, there's a few fields that are common: command field, version field, and an MBZ or must be zero field, followed by one or more route table entries. A route table entry can either be an actual network prefix, or it can be a next hop route table entry, which of course there would only be one because a RIP update only contains a single next hop for all the route table entries that it contains. And the next hop route table entry is differentiated because its metric is 0xFF. Otherwise, route prefixes, route table entries, have a valid metric anything from 1 to 16. Next, we're going to talk about BGP, Border Gateway Protocol. You may already be familiar with the function of BGP, and the purpose here is not to discuss how BGP operates in general. RFC 4271 described BGP not necessarily just in an IPv4 context, but a protocol that can be used for a variety of things. What we're talking about specifically here is using BGP to carry IPv6 prefix information, either within your same autonomous system from an iBGP session or between autonomous systems with eBGP sessions. So how do we know just what this particular BGP session is for? As it was determined that BGP will be used for other things, RFC 3392 brought into effect a capabilities advertisement. The capabilities advertisement is used in the BGP open messages, and it allows a speaker to communicate to its peer just what capabilities it's going to support over that BGP session. So when the BGP session is brought up, it will include the capability defined by the capability code and then length and value. The capability code value 1 is what's used when we're wanting to carry IPv6 routes in the BGP session. So capability code value 1 is multi-protocols extensions for BGP, and it's defined by RFC 2858. So a BGP speaker would use multi-protocol extensions capabilities optional parameter type 2. Usage of multi-protocol BGP is often referred to as BGP4+, includes carrying IPv6 routes, MPLS labels, and possible other VPN, virtual private network route information. So carried in the parameter value field is one or more combinations of a capability and value. So you would find the capability code equal to 1 for multi-protocol extensions. Capability length would be equal to 4, meaning there's 4 more bytes of value. The value would have an AFI, address family indicator, and sub-ASI field. The AFI would be set to 2 for IP version 6 as opposed to 1 for IP version 4. And then the sub-address family would indicate if we're using this for unicast, multicast, or possibly even both types of prefixes. So once we open the BGP session using the additional capabilities described before, we're now going to exchange update messages, which actually advertise, or it can actually unadvertise routes. For that purpose, we send update messages to transfer routing information between BGP peers. An update message contains 3 types of things, either unfeasible routes, network layer reachability information, which are actually IPv4 reachable routes, and path attributes. Update message path attributes are also TLV encoded, so that makes them variable length, and a variety of different type of attributes can be communicated. As we can see, normally with IP version 4 only, attributes define properties of the routes, such as what autonomous systems they were learned through, what the next hop is, maybe some other parameters that we can use for route selection. But with IP version 6, the path attributes actually carry the network layer reachability information for IP version 6, in other words, IPv6 prefixes. So the network layer reachability information in the update message itself is not used to carry IPv6 prefixes. The withdrawal routes and the network reachability information in the update message is used for IP version 4 addresses, whereas IP version 6 addresses are actually carried in the attributes. So again, not going to cover the BGP protocol in detail here. You're probably familiar with some well-known attributes and some other uses for attributes with BGP. As we can see, attribute types 14 and 15, which were defined in RFC 2858 as the multi-protocol reachable network layer reachability information, as well as the multi-protocol unreachable network layer reachability information, are used to carry IPv6 prefixes. So this is the format of a network layer reachability attribute, and you can see that it contains such things as the address family identifier, sub-address family identifier, as well as a network layer reachability information, in other words, the IPv6 prefix. So a single BGP update could have a long string of these attributes, so to speak, in the update, each one coding a different IPv6 prefix. So this slide just talks about more detail in terms of the field definitions of a multi-protocol reachable and LRI. The address family identifier, of course, would be set to 2 for IPv6. The subsequent address family identifier could provide additional information about the type of NRLI carried. There could be a next hop to contain the next hop of the address that should be used as the next hop to the destination, subnetwork points of attachments, and NRLIs are feasible routes that are being advertised in this attribute. As we discussed in the IPv6 addressing architectural topics of this course, there are 3 different types of unicast address scopes, either a global, site local, or link local. BGP4 makes no distinction between global and site local addresses. Of course, it's up to the network administrators to respect the address scope restrictions. In other words, don't advertise out a site local address into the global internet, for instance. Another limitation is only use link local addresses when generating ICMP redirect messages. Link local addresses are not well suited to be used as the next hop attribute in BGP4 for obvious reasons. So BGP4 is sometimes necessary to announce the next hop attribute that consists of a global address and a link local address. So constructing the next hop field with IP version 6. A BGP speaker shall advertise to its peer in the network address of the next hop field the global IPv6 address of the next hop, potentially followed by link local IPv6 address of the next hop. That could be differentiated by the value of the length of the next hop address field in the multi-protocol reachable NRLI attribute. It would be set to 16 when only a global address is present, or 32 if a link local address is also included in the next hop field. A BGP speaker would only include the link local address if it shares a common subnet with the entity identified by the global IP address carried in the network address of the next hop field and the peer of the route being advertised to. As a consequence, a BGP speaker that advertises a route to an internal peer may modify the network address of the next hop field by removing a link local IPv6 address of the next hop. A few additional rules for carrying other attributes. Of course, when BGP is carrying IPv6 prefixes, it is considered an other attribute. An update message that carries the multi-protocol reachable NRLI must also carry the origin and the AS path attributes, both in its eBGP, external BGP, and iBGP, internal BGP messages. Also, in iBGP exchanges, such a message must also carry the local preference attribute. An update message that carries no network layer reachability information other than the one encoded by the multi-protocol NRLI should not carry the next hop attribute. And a few transport considerations. As we discussed when we were talking about the IPv6 header structure, there were some modifications that needed to be made to the upper layer protocols. In the case of BGP, only using TCP, okay, so we only consider that. TCP connections on top of which BGP messages are exchanged can be established either over IP version 4 or IP version 6. But when using TCP over IP version 4 as a transport for IP version 6 reachability information, additional explicit configuration of the peer's network address is required. The BGP identifier is actually a 32-bit unsigned integer exchanged between two peers at the session establishment time within an open message. And finally, the use of TCP over IPv6 as a transport protocol for IPv6 reachability information also has the advantage of providing explicit confirmation of IPv6 network reachability between two peers. Next, we'll discuss OSPF for IP version 6, which is defined by RFC 5340 and also referred to as OSPF version 3. as opposed to OSPF version 2, which was used for IPv4. OSPF version 3 operates very similar to OSPF version 2. It is a link state protocol, so therefore it sends topology and prefix information separately. There are, however, new LSA link state advertisement types defined for IP version 6. And protocol processing is per link, not per subnet, as it is with OSPF version 2 for IP version 4. So IPv6 uses the term link to indicate communication instead of network and subnet. Interfaces connect to links. Multiple IP subnets can be assigned to a single link, and two nodes can talk directly over a single link even if they do not share a common IP subnet. Some of the differences with IP version 4 or OSPF version 2 is there has been changes in the authentication scheme, packet format changes, LSA format changes, how do you deal with unknown LSA types, the way stub areas are supported, identifying neighbor routers by router ID, protocol processing is per link, not per subnet, removal of addressing semantics, addition of a flooding scope, explicit support for multiple instances per link, and the use of a link local address. Similarities between OSPF version 3 and OSPF version 2 are depicted here. Basic packet types are the same. Hello, database description packets, link state requests, link state updates, link state advertisement packets. Those 5 are very similar. Mechanisms for neighbor discovery and adjacency informations are the same. Interface types, point-to-point, point-to-multipoint, broadcast, non-broadcast multiple access, and virtual links are similarly implemented with OSPF version 3 and OSPF version 2. The LSA flooding and aging techniques are the same. Nearly identical LSA types, and both use designated routers and backup designated routers for transit or broadcast links. So as mentioned on the previous slide, the OSPF version 3 packet types are similar as with OSPF version 2, so you have the same 5 packet types, but some fields of course have changed. All OSPF version 3 packets have a 16-byte common header as opposed to the 24-byte common header in OSPF version 2. So it's quite interesting. They managed to come up with a way to shrink the common header. So your packet types, 1 for hello packets, 2 for database descriptions, 3 for link state requests, 4 for link state updates, and 5 for link state acknowledgements, are similar but have a little bit different structure with OSPF version 3 than with OSPF version 2. Thank you for taking the time of viewing this topic of the Demystifying IPv6 course on IPv6 routing.